Hi everyone. So we're in the session 3. Today we will talk about finite volumes. Today and also the class of next week. So this is a very exciting session because in here you will really have a taste in your mouth about what is actually CFD. So really, I hope you enjoy this, and this is something that I developed together with Kilian Ferna. We put a lot of effort because it's not easy to have just a finite volume scheme that work with two-dimensional system that is not with non-Cartesian meshes, with something that is not just a square, something more complex. But it's still that is easy to be written and in a very clear way in MATLAB. Okay, so well, I hope you enjoy. So yeah, we are in the finite volumes part. This is again the repetition of the outline. The Green's functions will come at the end. We will talk about solving a linear system in 3 weeks and about the unsteady problems. Okay. Um, this is something we saw last time. So we have a Cartesian grid because we had a finite difference scheme that is very appropriate when we consider grids where the faces are aligned with the frame of reference. For example, when you have Cartesian coordinates or polar coordinates and you use cylinders, spherical coordinates, you use spheres and so on. Okay. There is another numerical scheme that is called finite volumes, where you actually can have something that is more complex. In the class of today, since we are treating a two-dimensional system, we will have this kind of, for example, profiles. We can already do these kind of things, the airfoils. But you can also think that we can actually represent three-dimensional systems in terms of axisymmetric systems. So we can have actually burners or maybe nozzles, like this one. This is already encouraging so that you can start thinking about your projects. Let me tell you that I have already written a journal paper with one student who did a finite volume representation of a three-dimensional axisymmetric system. So this is something that we can do with our code that is actually built by yourselves, your own code. This is the kind of mesh we will actually consider this time. Okay, so I just did it somehow very deformed so that you realize what we are actually looking at or pointing, aiming at. And we will consider this kind of situation. So we are sitting inside a control volume in here, and we actually express our differential operators, derivative Laplacians, with respect to the neighbors, which are actually in this case 3, 6, 8 nodes. Okay, in order to have a better understanding of the methodology, we will still consider a non-Cartesian grid, so something that looks like this in a much more organized way than the thing I just showed you before. But it doesn't mean that it does not apply for the mesh I just showed you before. Okay, we will just do the derivation from this kind of system, but it actually is okay. It can be applied in more complex geometrical domains. And this is, if we just visualize the 9 nodes I just showed you before, we have the same situation here. We have the node P and the 8 neighbors if we're looking at this region in here. Okay, so the first thing to point out is the notation. So the notation in here is similar as the one we use in finite differences. We have P, we have east, we have west, north, south, but also we have southwest, northwest, northeast, southeast. And something else to point out is that we will have control volumes. So in this case, in our course, we will talk about control surfaces because we're in a two-dimensional system. Okay, so this is a control surface around the node P, the node of interest. And this is you could look at these steps like a recipe, but I don't like it that you look at the recipe, because a recipe is something you do without understanding. Okay, so you will see that these 4 steps, they come just naturally as we do during the process of derivation. Okay, so we will now go into the virtual blackboard and do some derivations. Okay, so we will just consider the control volume as I just showed you before. Okay, why is all this? So we have here the control volume, and we will call this P. And the equation that satisfies this, if you remember the first class about how to derive a partial differential equation, you remember that we were at some point in this case, we were T dV before shrinking the control volume, if you remember that step. And we have lambda here, and this is equal to the source. Right now we don't care about sources, so we just put this to be 0. Okay, but what we want to have is a differential definition of the derivative, so at P, which means that we want to have something like this. So if you make the relation, the analogous comparison with respect to finite differences, this is what we need. We need a numerical scheme, so like a stencil, an equation that describes the derivative, or the second derivative of temperature at the point P. Okay, so right now we will consider this, how we actually go from here to here. And this is just thinking about, let's say, numerical integration. And this is something also very interesting if we just look at it in a very pragmatic way. So we have here, let's assume we have a function, and this is going to be x, this is going to be the function, let's call f of x. And we have okay, we have here a function, for example, like this. And let's assume that we're interested in making the integration of this point. So here, and this is as a distance, let's call it delta x. Okay, so this is what we want to do, and this is fx. Okay, I hope this is can be seen. Yeah, okay. What is the very simple approximation? A very simple approximation would be the midpoint rule, which means that we will just place ourselves here in a point P, and this is going to be the corresponding f of xp. Okay, so a very simple approximation is based on the midpoint rule. So this approximation is equal to f x p multiplied by delta x. Okay, so let me just, yeah, I think you understand. This is over this region AB. Well, you could use something much more, let's say, fancy. You can use also a trapezoid rule. If you remember maybe your courses, instead of having just one point, you just consider maybe 2 extremes, and maybe the integration is what is going to be more accurate. But right now this suffices for us. How then we can actually relate this with the previous expression we're interested, which is this one. Okay. So we say, let's put it in here. We say that this is the function of t dv is equal to a delta volume, and the function of t evaluated at p. So basically we have this at p is approximated 1 over delta volume and this is the first thing we have to consider. Okay, and this is over the volumes. I will just write it in here, the volume in p. Okay, so let's write again the equation we just have. So at p is equal, now I will just do a little change. So is, since we're in 2 dimensions, then we have just a control surface, and I will have okay, the notation here is that this is a superscript, and we have here lambda. So remember that we are in a control surface, so this is ds, this is around sp. Okay, this is what we just saw before. What is the next step? Actually, we are going backwards. We are going backwards when we're deriving a partial differential equation from integral like conservation law. We are now going from a PD to the conservation law again. So this is going to be, let me just forget about lambda. So we will have this equation, and we will have then instead of a control surface, we will have an integral over the line. Okay, so if we had a control volume, here, then this would be like a control surface. Now that we have here a control surface, this is like a control line, let's say, if you want to think it in that way. And some of you had already maybe predicted what is going to happen. We will just apply the divergence theorem again, but now in this way. So it's like going backwards in time as we did in the first class. Okay, so this is how it looks like. Now let me show you, so in a more beautiful way, this thing. So we just go from here to here. Therefore, the actual expression we are actually looking at is this. And just to be consistent, this is a little mistake here. Okay, lambda. Okay, now the idea is to go from an integral that is related to this contour surface here. We will split it in these 4 phases. So we'll have an integral that goes from southwest to southeast, then southeast to northeast, northeast to northwest, and northwest to southwest. Okay, let us now just pick one term of this. We will just pick this one. These other 3 they will be actually derived in the same way. So let's take this one. Anyway, before actually analyzing that term I just showed, let me just first talk about the normal vectors. This is something that is crucial for the correct implementation of finite volumes. Okay, let's start with something very simple. We have, imagine we have this kind of this slope like this. So this is actually like the hypotenuse of a triangle, and we will just picture here the normal vector n. Now let's put some numbers to make things clear. Let's assume this actually is 1, and this is I don't know, let's put it 4, like this. Okay, so give me the coordinates of n. And what about if the normal vector is actually normalized? So I don't know if you remember this notation that you may have learned so far in previous courses. So this is a vector pointing in the x direction. This is a vector pointing in the y direction. So if I do this, so maybe some people say, okay, but this is actually simple. This is something like this, and that's the end of the story. Okay, this is completely wrong, no? You already realize why. So this is wrong. So we have, let's be more patient and let's look at the truth. So the first thing is that the normal vector is pointing in this direction, in x, in the negative direction. This is negative, and is related to this. So actually is related to 4 in the x direction and to 1 in the y direction. So the right thing to do is to do something like this: minus 4i plus 1j. This is actually the normal vector. Okay, and if we want to normalize it, what we'll do? Well, we just divide by the norm, which is going to be, so the square root of 4/2 plus 1/2. Okay, so this is how it should be thought. Now let's be more abstract. It's not going to be a big change, so no necessity to be scary. So this is going to be x, this is going to be y, and this is going to be n is equal. So what is going to be there? The normal vector. Yes, it's going to be minus x in I. No, I screw it up again. You see, it's easy to screw it up. Minus y in A plus x in J divided by the norm. That's all. So this is how a normal vector should be represented, okay? But we can do something even more nice, more interesting. Okay, so let's assume right now this just make part of a larger object. So this is gonna be like this, well, something like this, something like this, something like this, and we will just give the previous notation. So it was south, southwest, southeast, northeast, and this is north, northwest. Okay, so this is gonna be our normal vector of interest here. And now express this x and this y as a delta x and a delta y. So in that sense, our expression would be minus delta y I plus delta x j and the norm. But now we can do things interesting if we actually define in a much more accurate way this delta x and delta y. Okay, so we will say something that will take into account that we are actually taking into account the counterclockwise notation, and this is very important. So let's me call delta x. We will just make the notation from northeast to northwest, and we will call delta y also from northeast to northwest. Like this. In here, we will define that this is going to be northwest minus northeast, and this is northwest minus north. Okay, the same thing actually. Well, what does it mean here? It means that in this case, this quantity is actually positive, and this quantity is actually negative. Actually, both are negative. I'm silly. So based on that definition, then our normal vector is going to be delta y e minus delta x j and the norm. Okay, so then the norm, well, let me just write it quickly. So this is the normal vector if we actually have this definition. So northeast, northwest, northeast, northwest, and so on. Okay, but the nice thing is right now, if we keep the same convention of this counterclockwise, we can describe the normal vectors of at any position in the same way, with the same array of signs. So let me just shrink this and write another example. This is northeast, northwest. Now let's just do, for example, the other one. Let's do southeast, northeast, and just without paying too much attention, I will do this. So southeast, northeast minus delta x, southeast, northeast j over the norm. So okay, the norm is delta x squared, so this is also, well, the same thing. Southeast, northeast plus southeast, northeast. So we have used the same convention in here. Okay, plus minus plus minus. This is actually true. Okay, let's see. Let's actually verify. So we will consider here what is y southeast, northeast, x southeast, northeast. So this is actually x south northeast minus x southeast, y southeast minus y northeast. Sorry. Well, northeast, southeast. Okay, so now that you look at this figure, you can tell me if this is the first term is positive or negative. Okay, know that x north is smaller than x x northeast is smaller than x southeast. Okay, just because I mean we have this convention xy. Okay, just maybe I didn't say that before. So this is actually negative. And now this one, northeast plus minus southeast y southeast, this is positive. And just by looking at this arrow, so this is the arrow that is north of southeast northeast. Looking at this arrow, you will see that there is a positive change in x and a positive change in y. Okay, so the two components of the vectors are positive. If we look at this, we have the same situation, because this is actually positive already, and this one is also positive, because in here we have a negative value times negative, you have a positive. So it's just to show you that this convention holds as long as we have the counterclockwise notation consistent all over the place. Okay, so be already aware that this definition of distances, deltas, they can be positive or negative. Go to the next slide. So this is in a more beautiful way how things actually are written down. So the normal vectors for all four phases of our contours for phase. Okay, so we already know how to derive the normal vector. So as I told you just before, we will just pick this term and continue the analysis. Okay, so let's write it down. So we have here L S W S E. Just for the to make it things simpler, we will just forget about lambda. Let's consider lambda equal to 1. Okay, anyways, we consider it constant in this derivation. So we will have this, and this is what we want to actually derive. Here, therefore, when we have the normal vector associated with that phase. Let me just write in here. So this is the normal at the south phase. Which is nothing but delta y SW SE minus delta x SW SE over the norm, the length of that phase, which is LSW SE. Okay. So now let's decompose this term by doing just dt dx dt dy. Okay, and this is the dot product with delta y SW SE minus delta x SW SE over the length, and this is the L. Okay, now we have just to do the corresponding dot product. So we will just take this thing out from the integral. We'll have 1 over L SW SE multiplied by L SW SE dt dx delta y sw se dl minus 1 over, so again here the length dt dy dx sw here se dl. Okay, this is on lw se. So we have this thing already. Actually, I could have done it much easier. I will just show you it in a second. Okay, what I just did was to rewrite this expression in here. So I just took this delta y and delta x out of the integral because this is a constant number. And in here we have it written down in a more beautiful way, like this. So this is what we have just did. Okay, so in your opinion, you guys that are behind your screens, you have to tell me what is the next step. What do you think is the next step? We have this first term in here, the second term here, and now we have to integrate in this thing. But as we just said at the beginning of the class, this is something we can do it in an approximate way and still remaining with a certain good accuracy in the derivation. Of course, that depends on the size of the cells, as you will see. So we have a numerical integration, and as I pointed before, we can do several rules: the midpoint rule, the trapezoid rule. We can even go to the Simpsons rule. So when you have more points, reference point along the integration domain. In this case, we will just be based on the midpoint rule. So let me just draw here again the phase we are interested in. So this is the phase at the south. We have SW, we have SE, and we have the normal vector, which is NS. Well, right now I have to remind you with something. So this is the grid we are using. So the grid in which we base our derivation. And now we have to have clear in our minds that these points in here, they are not nodes, okay? They are auxiliary points. The only nodes in the derivation are these black dots in here. What is the notation that differentiate between the auxiliary nodes, or the auxiliary points, and the actual nodes? So the nodes we will have it with a capital letter. So in here, for example, this is a big N, this is big S, this is big NS. No, this is actually not. What is this? You know already, I assume. So this is northeast with big letters, capital letters, northwest, and so on. Here, for example, what is going to be this one? This one is going to be, this is an auxiliary point, and it will have capital letter, but a small and letter denoting east. Okay, now we're in the midpoint rule, and we are interested in this phase, in this one in here, and we will have the approximation of saying that this is the midpoint. So we will refer this as a midpoint. It's going to be S. Okay. Note, for example, that in this case, the this point is not exactly in the middle. But anyway, this is the approximation. We are just stating that, as I, let me just picture it here, we're making the integration of that function between SW and SE, and this is gonna be, let's say, in here south, because it's not exactly in the middle. But we say that the integration we are interested in is gonna be the value of this function. This is the function at this height, and then let's multiply it by delta. In this case, let's call it delta x, or the distance. Okay, so this is gonna be the value of our integration, the distance between SW SE. So this is why it remains approximation. Now, when we reduce the cell width, then this integration becomes more precise. Okay, so this is just to let you know where we are defining the midpoint in this case. So this is gonna be south. Okay, so we'll just write the whole thing. So we know that this becomes dt dx, where at south integration dl, okay, over this lsw se. And here this is a similar thing, dt dy, where at s, and then integration, oh my god, this is, yeah, integration dl sw se. And what is the value of this? This is nothing but the actual length. The same here. Okay, now we have here again written this down in a beautiful way so that it's more clear. Here we just consider lambda. Okay, so we have introduced lambda in the whole expression. That's all. Okay, now we are not following a recipe, just I told you. We are just following our intuition, our analysis. What is gonna be the next step right now? So what is the thing we have to do? So this can be already be computed directly, because these are knowns. This is just because of the mesh. We need to compute now these ones, okay? And now we have to base our knowledge on an additional theorem, as we will see. And this theorem is the Green's theorem. So this is, you can go to Google, Wikipedia, for example, to see the demonstration of this theorem. And this is what we will do. Something to take into account is that right now we have actually a line integral, and this is something we didn't have before. Maybe this is interesting to point this out. Before, we have integrated on the surfaces, and the integral, for example, in this side was integration, and we have this notation here, SW SE, because basically what we were doing was to compute the flux through these phases. And that's why we were using this notation. Right now things are not the same, because right now we will integrate along the surfaces. So in this case, right now we will have the corresponding control surface, and we will integrate along the line. Okay, So remember, here we have normal vector in this case. Here we don't have any normal vector, we are just integrating along the lines, and this is the main difference. Okay, let me just write this thing here, just well, let's pick one of these, the other one is going to be basically the same, so we will pick this one. Okay, well, actually we can just do both. This is pretty quick. Before going to the blackboard, just something to say, which is actually pretty important. Remember that right now we are standing at S, so we are standing in this point. Okay, and now this line integral is defined along the contour surface that surround S. So the surrounding of S is in here. So this is not exactly the same control volume as we had before. The one we had before, it was called S superscript P, and was this one like here that I'm just showing. Right now is the one around S. So this is not the same control volume, okay? Okay, so let's concentrate right now in these two terms that I'm pointing here, this one and this one. Okay, so we have this over the surface, along the surface S TDY, and here the same thing but TDX. What do you think we have to do? Okay, right now we just split the integral in how many integrals? We have how many faces? We have 4 faces. Okay, so we have 1, 2, 3, 4. The same for this one. To have plus, plus, plus. And here we have T and the X. Oh, sorry, let me just write it down quickly. Okay, wrote it down. So the integral in here, we can start in this point. We can start from here to here. Remember that we are integrating following the convention we showed from the beginning, the counterclockwise convention. So let's write it. It's gonna be from SW, and you have to be very careful when you actually write a capital letter or a small letter. Sometimes you should exaggerate maybe, so that things become clear, not confusing. So SW, SE, now we go from SE to E, then from E to W, then from W to SW. So we close the loop. And here we do the same thing behind. SW, SE, and so on. So we have the equations. What is the last thing we have to do? Yes, we need to integrate. Again, we can use the midpoint rule. Okay, so before continuing, let's just write the labels for these. Okay, the nodes we should know, and the auxiliary points as well. So we have said this one here, I will just make some assume. This is what? Yeah, capital S. Here is, yes, P. Here we have so small s, small e. Here we have Yeah, so we have small s, small w. So these are the points we're interested in right now. Now we will apply the midpoint rule. So you have to tell me this is going to be evaluated, this t evaluated where? Think. We are between SW and SE, capital S, small e. So this is gonna be around S, which is the large one. This one is going to be between SE and E is gonna be in small se. This one, the next one, is going to be between E and W, therefore is at P, and the last one is between W and SW is gonna be small SW. Okay, the same for the one below. Okay, we should note right now that we just did an approximation, therefore this equality doesn't hold anymore. We'll just erase this. Oh, it cannot be erased. Okay, we'll just write it on the top. So this is an approximation right now. Okay, well, and let's write it. So t d s e s s t d y approximately. Now since t is constant right now, is just the value at a given point, we can just take it out. T at capital S, and this is gonna be ty sw se plus t in small se se e dy, and so on. So I will just write it down quickly. Voila, so we have these good expressions, and finally we just write the final expression. So this t dy t in s. What is this? The integration of this? Yeah, exactly. You just is the distance delta y between sw se plus tse delta y se e and so on. Okay, so we have here the expression of this one, and we can do exactly the same to derive the other equation. So let's show let me show you how it looks like in when they are beautiful written. Okay, so we have the first expression we just did and the second one. Do not forget about this sign. Sometimes students forget about the sign, things doesn't work, and they look and look and look, and at the end realize that this is just because a little sign was missing. So we can continue with the other terms, and for the other terms, for the other phases, we were just considering this phase in here, if you remember, this one here, but we need to consider the other phases surrounding P. Okay, so as you can see in this slide, you can define the associated or the corresponding controls or phases. So I encourage you, so this is something, so you're supposed to watch this video days in advance. So I really suggest that you can go through the procedure I just show you and try to derive these terms in here. just to cross check that you understood. You can also look at the scriptum for some help and compare your results. So basically to arrive prepared to the day of the practicum. And this is what is waiting for you in the practical session. So this is the question we have just seen. We consider just one additional simplification in the derivation was to actually have this conductivity out because we consider this conductivity to be constant. However, well, in the projects, I have had several projects already where the students wanted to solve the heat equation, but considering conductivities that are not uniform. So you can remember the finite differentiation. In this case, we have to consider lambda inside and therefore make some little changes in the derivation I just showed you before. But it's not, I mean, it's just an additional change, not much. You can also, there are a lot of different physical phenomena that are described by the Laplacian. So this is a kind of Laplacian. For example, the acoustic equations, the wave equation, you have here, instead of T, you have here pressure, the acoustic pressure, and you may have here, instead of lambda, the speed of sound, for example. And the speed of sound can change in the domain, so you can actually have the speed of sound also inside in here. So the equation will look very actually the same, but now you are describing a different phenomenon. So just to make you aware that this is something that is not only focused on the heat equation. There's a lot of physical phenomena that you can play with and investigate. Okay, so this is gonna be the fin. So before, in the finite differentiation, we consider a square fin. So the square was like this. Now we can consider a trapezoid, and you can go even more crazy. Students like to do that, and I like that they like it, is to consider different shapes. Now you have a scheme where you can actually consider shapes like this one, like this, for example, sorry, like this, or like this. Just, it would be nice. I mean, you can play around and see what are the shapes you want to have. You can also have something that is completely non-symmetric, so you can have a fin like this, whatever. Okay, but in the exercises we will concentrate on something more classical, so just a trapezoid. And when we will have the boundary conditions as here suggested, the isothermal, then you have the conjugate heat transfer. So here you apply Dirichlet boundary conditions, Neumann. Now, maybe we will talk about the exercise during the meeting before the exercises, but just maybe I will forget, so I will just tell it right now. In order to do the thing, we can just do the half because we consider this to be symmetric. Therefore, our domain is going to be actually this. And since we are applying a symmetric boundary condition, we will use the Neumann boundary condition in here. Okay, this is going to be actually very similar to applying an adiabatic boundary condition at this phase, when you consider just half of this as the domain of interest. And once you discretize, this is how it should look like. So you have here some temperature distribution, temperature distribution from hot to cold. Then you have here, you can imagine this as iso lines of temperature that will be perpendicular to this surface in here because you are imposing here heat flux equal to 0. So this is something we will discuss, but you have to be already aware to how to evaluate the correctness of the results based on the results. So you have to be capable of saying, I'm getting results, but they are garbage because they are not actually doing what they are supposed to do. Sometimes you have to have this intuition to evaluate how good the results are. And the basically thing you do to evaluate something, the goodness of a result, is at least to see that the boundary conditions are satisfied. This is the first thing you have to do. That is a quick check. So you have to check, yeah, here the temperature is what I impose, here the normal boundary condition is clear because the ISO lines are normal to the surface. The roving is a little bit harder to evaluate, but you can do some tuning on this heat conductivity coefficient, they and see how flux is occurring in this surface. So this is something we will discuss also in the meeting before the exercise. And this is just to remember that we have maybe 1-2 more weeks to actually define the projects for each group. And this slide is gonna be filled in some weeks, okay? Actually, normally in the normal course, so the next class is something with the considering the actual boundary conditions. Something I didn't say right now is that this class, so the third session, you consider very simple boundary conditions, Dirichlet, just to enter into this finite volumes world. And the boundary condition is gonna be for the next class. You have 2 weeks to make all this assignment I presented today. So since we will have some time for lecture next week, then I will talk about some ideas I have that can be interesting for some of you in terms of projects, acoustic phenomenon, hydrodynamic phenomenon, combustion. So we will have to see, but I really encourage you that you already have to bring your own ideas. Most of the time, the best projects are the projects that you actually suggest. Maybe you are doing a master thesis, a bachelor thesis, or you are just curious of knowing something. Even I have had some PhD students in the class, and when you are interested in something and you apply this knowledge on this thing you are interested in, things actually become super nice. So okay, so this is just to push you a bit on this. Well, thank you very much for your attention, and let's see each other on Friday. Bye bye.